Alright, I want to look at AC resonance curves here. We did a little bit on AC resonance just with the phases and working out what it was and the formula. I think you know that the formula now is F0 equals 1 over 2 pi square root of LC. So if we're going to draw, often these curves are done where what we're measuring is current against frequency, and we get a curve that looks like that. And what we say is that this peak here is the resonant frequency. We'll call it F0. The whole scale is F, and that's going to be according to this little equation here. Now that means that this curve here is for a certain LC combination. Right, so the LC combination is fixed, and what you've done is you've just adjusted the frequency until you found this resonant bit here. And so if we had a different LC combination, we'd have a different curve. So obviously if we had a different LC combination, we could have a higher frequency. To get a higher frequency for the resonance, obviously we'd need these little guys, the square root under here, to be smaller. Now getting back to this original one, if I look at these 2 points, these are lower currents and they're different frequencies. One, we get a lower current when we've got a lower frequency, and one we get a lower current when we've got a higher frequency. So we go back to our reactance for our inductor and our reactance for our capacitor, and we ask ourselves what's happening with these circuits, and we can see that at this point here we've got a low frequency and yet we've got a high current. That means the circuit's no longer in resonance, which means either the inductor voltage is low, like this, and the capacitor voltage is high, or the inductor voltage is high and the capacitor voltage is low. Now this situation here is going to be for both these points here, but the question is which one's which. So if we're asking when does the capacitor voltage get high, causing the current to be low, is, well, if we're looking at the capacitor formula, the capacitor voltage gets well, the capacitance is fixed. I told you this circuit has been fixed. So we're saying when your frequency is low or small, then your reactance is high, smaller f, higher xc. So the xc is directly with the current going to cause the Vc, therefore the big Vc, this one, is this one. So this is the capacitive side. That's the capacitive side. A little bit, you know, you've got to go through a couple of mental steps to do that. We said that the frequency was low, therefore xc is high, therefore Vc is high. Now the thing is, when you decrease the frequency with a circuit, what happens to XL? Well, you decrease the frequency, XL gets small, that means VL gets small. So we definitely identified that the low frequency corresponds to a small VL and a big VC. And the other point we can see is a higher frequency. Higher frequency gives XC being smaller, higher frequency makes XL being bigger, therefore this point in the circuit is the inductive part. Right. Now when you look at these guys, the steepness, like if you actually look at these two, the steepness of this peak gets given a Q factor, a quality factor, and that all depends on how steep. So that's a quality factor. I'm not really going to go into that, I'm just letting you know. You can look into it if you want. There's another way of looking at these circuits, which is when we want to, and I've seen this on School Questions, is they might ask you to plot the phase angle. We'll draw some axes. They might ask you to draw the phase angle of the circuit against the frequency. Now with our phasor diagram on these little guys here, we could call this phase positive, we could call this phase, negative. Right? Are we good with that? And so what we could ask ourselves is, and we can see it here, as we increase our frequency, there's a point at which, f0 if you like, where the phase angle is 0. We know we're going to get that point, right, because that's when we're in resonance. So this would be f0. So as we found our frequency here before was lower, was a capacitive circuit. If you've got a capacitive circuit, the vector's down here, the V supply is closer to the VC, and that's a negative phase angle. So we're pretty sure it's going to look like that. And as we pass through and become inductive, the phase angle is going to be like that. So that's just plotting phase angle against frequency. Sorry, negative. While we're on about that, what we find with these, with a motor, is you often have a motor being quite like that, with very high VL and very, well, just a very close VS to your VL. Very inductive because it's coil. Now that's not so efficient, because we've seen that's when you've got more resistance in the circuit. More resistance means less current means less torque, right? Because torque was equal to Benny. Remember those two Swedish guys? Benny and Borny? Benny and Born, actually. So the torque equals BANI, I being current. Larger current, larger torque. So what they often do is they stick a capacitor on a motor, and what that's going to do is give you a VC, and that's going to bring your VS down closer to your VR, giving you the VR equals VS, getting your phase angle down to 0, and that's going to give you much more efficiency. So that's a motor with a capacitor. What we also see, just get another page, is these tuned circuits. So often what you've got, this is like a symbol for an aerial, you can make a circuit like this, right, underground. That becomes your aerial. This is a tuned circuit, and so what we're saying is that the RC combination is going to give you a resonant frequency. At that frequency, the currents here will be greatest. So we can take our signal off here, and we usually do this with a detector, and we've got a radio. Now, where the current is going to be strongest at the frequency you're trying to tune. How you tune it is with a variable capacitor. And these guys are around about 30 to 50 picofarads for an AM station. So you could get a question like where they're asking you, okay, you want to tune from maybe 500 kilohertz to 1.5 megahertz. So that's 0.5 megahertz to 1.5 megahertz, or 500 kilohertz. And they would ask you if your capacitor or if your little inductor has how many henries, what will that do? So, I mean, looking at this, if we were round about the 40 picofarads, we could work out what size approximately our inductor would have to be to give us an F0 of around about 1 megahertz. So it's a tuned circuit for radios. Alright, that's all I wanted to do.